In this short video, I want to go over the first of two model extrapolation procedures that we're going to use to take the resistance measured on a model and use it to estimate the resistance of the full-scale ship. This one's known as Froude's method. It dates basically to his original idea, and it depends on his premise, which is that of the Froude we now refer to as a Froude decomposition. So if we look back at our similarity solutions, we found that the total resistance coefficient of a vessel for the problem we're looking at, which is steady state, quiescent C, is a function really of two numbers. So we added some additional numbers like Weber number, which dealt with surface tension, cavitation number, but the dependency on those is very weak. And so we're dealing with really these two fundamental numbers. If we could match these two in a tow tank, then we could measure the resistance of the model scale, compute the resistance coefficient, and that would be the same as on the full scale, and we would immediately know what the full scale resistance is. However, we cannot match both of these at the same time. So we choose to match this, and we use what's called the resistance decomposition to actually get an estimate of the total resistance of the full-scale vessel. The resistance decomposition looks like this for the Froude's method. And so how this decomposition, the nature of this decomposition influences the extrapolation procedure. So this is the one used for Froude's method. In Froude's method, the Froude decomposition takes this total drag coefficient, which is a function of Reynolds and Froude, and divides it into three pieces. A frictional component, which is a function only of the Reynolds number, a wave component, which is a function only of the Froude number, and a constant component, which incorporates essentially the viscous pressure effects, the wake effects, or what we call form drag coefficient. That is assumed to be constant. It's not dependent on anything except for the hull form itself. And so since the model is isometric, or it's a geosimilar of the full scale, then C form is the same for model and full scale. We lump these two pieces together, the wave drag and the form drag, and refer to these as a residuary drag. It's the drag you're left with when you take friction away from the total. And so that we're going to give it the subscript R for residuary, is the wave plus the form. Now, since the form on the ship and the form on the model match, because they're constant, and we are using a geosimilar hull, so they're a function only of the hull shape, which is the same on model and full scale, and the wave drag and wave on the model and full scale match because we're matching Froude. We're using Froude scaling. So Froude is matched, so we're matching both of these components. This tells us that the residuary drag on the ship is equal to the residuary drag on the model. Now I just do some algebra. The total drag on the ship is equal to the frictional drag on the ship plus the residuary drag on the ship. And again, that residuary drag includes both the form drag and the wave drag. This is equal to the frictional drag on the ship plus the frictional drag plus the residual drag on the model, because these two things are equal. The residual drags match. And so this is equal to the frictional drag on the ship plus the difference between the total drag on the model and the frictional drag on the model is the residuary drag on the model. So I can write it in this manner. And so I have the total drag on the ship is equal to the total drag on the model. Now I could stop here. If I managed to match Reynolds and Froude, we'd be all set because the frictional drags would also be the same. But we cannot match Reynolds, and therefore we have to account for the differences in the frictional drag. And that's what you're seeing here. This disparity in the frictional drag coefficient between the model and the full scale, or which has a subscript here, S, has to be accounted for. Plus, in our standard decomposition, our standard extrapolation method, we add on some optional stuff as well if you want to deal with appendages or air resistance. And in the case of the standard form, you account for a roughness of the full scale of a real ocean-going ship that has biofouling and other factors. You have to include an additional roughness, which is not present on the model itself. So this Froude approach shows a graphical demonstration of what's going on. You go and you measure. So this is Reynolds number down here. So this is log 10 RE. These old charts like this one, they used to write Reynolds number with a little n here. I'm going to write it as RE is the way it's written now. And this is the total drag coefficient here. Actually, these are various drag coefficients here. So I just wrote C, and this is times 10 cubed. So we're going to see this times 10 cubes or times 1,000 a lot, because typical drag coefficients are things like 0.002. Instead of writing 002 all the time, I would rather just write 2 and then you have to note your chart that you multiplied everything by 1,000 to make it look nicer. The numbers look nicer to be able to have a 2 here instead of a 0.002. So we go and you measure. If I start on the ship side, here are the actual Reynolds numbers of those different design speeds that I'm interested in. Now, I match Froude number, and the result of the Reynolds number, the models they're much smaller. Note this x-axis is logarithmic. So they're much smaller, several orders of magnitude smaller than the full scale. So these are our Reynolds number conditions. We match Froude. We have different Reynolds numbers. And these are the drag coefficients that you're getting. These are the total drag coefficients of the model that we get from non-dimensionalizing the measured resistance in the tank. And then we can see here, because this total drag on the model is made of two components, a frictional component and the residuary component right here. Now this residuary component in Froude's method is the same on the model as the full scale. So you take this blue arrow and you essentially translate it over here. So this is the same speed, or same Froude number on both these cases. To move that blue arrow over there. But the frictional drag coefficient on the model, these are drag coefficients, they're not drags. Drag coefficient friction at a lower Reynolds number, you get a higher frictional drag coefficient is higher on that model compared to the frictional drag coefficient on the full scale at this higher Reynolds number. And so the value, what we're trying to estimate, so we're effectively measuring this, and we're assuming that blue arrow is the same on both sides. And so where this lands over here is dependent only on the difference in height of the frictions, these two frictions, how far apart they are, plus this additional delta CF, which is for roughness, which we're going to add on at the end. So this total drag coefficient on the full scale ship is simply the drag coefficient of the model, plus the difference between the frictional, or I've written here as minus, so minus the difference between the model friction and the full scale ship friction, and plus this additional drag that we have to include for the full scale ship, which corresponds to roughness of the full scale ship. And so this we're going to measure. I'm sorry, that's not right. That's what we want to know. This we're going to measure. This we're going to estimate. This we're going to estimate. And these are, again, functions of Reynolds numbers. These are Reynolds number dependent. This we're just going to tag on a constant value, and we're done. And we have the total drag coefficient for the full-scale ship, and that we can convert to a total drag for the full-scale ship. Now, some caution here. These frictional drags for these methods that we'll be talking about, these sharp elimination methods, they do not use the flat plate Prandtl curve that we've been using. They use a slightly different curve, which is known as the ITTC 1957 line. This, again, is the International Tow Tank Conference, I believe, 1957 line. I've plotted both of them here so you can see that they're quite similar. Blue is the Prandtl line we've been using in class, that Reynolds to the 1/5 power line. The red is the ITTC 57 line. There's a range of Reynolds numbers over which they're almost precisely the same, and then they're different at lower and higher Reynolds numbers. They call this a model correlation line rather than a flat plate friction formula because it tries to incorporate some of the 3D effects on skin friction. And these are basically curve fits that attempt to better incorporate estimates of skin friction for real 3D shapes. There were a number of these lines over the years, including one that you may see in some of your reading, the ATTC. That's the American Tote Conference, 1947, also known as the Schoenherr line. There were even lines before that. In fact, Froude himself had his own friction lines that weren't Reynolds dependent. They were just dependent on flow velocity and size and stuff. But so over the years, these have been sort of come together, and then they've decided to have a standardized method, and that standardized method is this particular formula right here, which is the ITTC 57 line. You can see there's a log 10 Reynolds here in the denominator, and then it's quite close to Prandtl's formula, which depends over, is proportional to 1 over Reynolds number to the 1/5. So you have a very different functional form between these two, but you get very similar-ish looking curves. So this is what you're going to use in both of the model extrapolation procedures, not the Prandtl formula, this model correlation line. So here's a basic recipe, and we're going to run through a problem on Tuesday in the actual class, or at least online, when we do it online. You measure yourself the resistance, total resistance of the model. Then you convert the total resistance of the model to, you convert it to a total resistance coefficient. Sorry, it's getting late. And we do that by taking the total resistance of the model, dividing it by our usual 1/2 rho u squared. This is the dynamic pressure, but we use the density of the tank water. We use the speed of the model, and we use the wetted area of the model here to get the total resistance coefficient for the model. Then we need to estimate the frictional drag coefficient for the model and for the full-scale ship. So these require knowing the Reynolds number of the model and knowing the Reynolds number of the full-scale ship, popping in those formulas and getting these two drag coefficients. Now we have enough to compute the total ship coefficient is equal to the model coefficient minus this difference in the frictional coefficients. Then we add on the roughness allowance. In the standard Froude procedure is 0.0004, gets tacked on to this. This deals with roughness on the full-scale boat. Now we have the final total drag coefficient for the ship, and we convert it for a total drag to a total drag coefficient for the model of by multiplying by the dynamic pressure. Now this is the density of seawater through which the ship will be traveling. It's the actual ship speed, not the model speed, ship speed, and it's the ship wetted area times the ship total drag coefficient to give the ship total resistance, again, in newtons. And then you're done. And so in the lecture notes, I put an example. We're going to run through a separate example in class, which is a little bit more detailed. And we'll see you then.